Welcome to the another video of the basic electrical engineering. Here we talk about that what will be the instantaneous power that we got if we have the RL load and RC load, and assuming that the voltage is of reference with sine of omega t and the current is lagging by an angle of phi. Here the current is leading by an angle of phi if it is R and C, and if it is R and L, the current is lagging by an angle of phi. So we have written the expression for PRL and PRC here, and for the sake of clarity we can give it the nomenclature is L and here C, because if the voltage is reference is same, these two values will differ. So here we are just changing the nomenclature with IMC. And when we know the sine of A plus sine B, 2 sine A sine B will be cos of A minus B minus of cos A plus B. So we will just write down the same expression. Here we divided by 2 and multiply by 2. So we get here 2 sine of, so let us write. So we just take the solve with the equation. This is divided by 2 into 2 sine A sine B. So it will be a cos of A minus B. So it will be for cos phi and A plus B. So this term is added up with the minus sign here. So similarly this side also we get cos of minus phi, cos of 2 omega t plus phi. Now if we solve this, so what we obtain here is that we write it in terms of RMS value and V and IL. This is same meaning, Vm by root 2 and IML by root 2. So this will come as V and I. So we try to write it in terms of RMS values and cos phi and cos of 2 omega t minus phi. Here also cos phi minus of 2 cos 2 omega t plus phi. Getting this term as cos of minus phi is also cos phi. So we get to split this term. We got here one term is as a term Vi cos phi, another term we get which is depending on the omega t. And here also same thing, we got a fixed term. This is a fixed term, Vi is cos phi, because if the phi is constant, this value is fixed. This value we are getting change with omega t. So let us draw the waveform of it. So here we just have a waveform of the voltage waveform, because the voltage is the sinusoidal waveform and it is a reference waveform. So Vm sin omega t is written on the dotted line of Z in the waveform of V. Here also we make the waveform of V, and here we have this value is pi. Obviously this value is 2 pi. Sorry. And here is pi and this is 2 pi. And the current is the lagging by phi, and this current is C. This is leading by phi. Also we get to obtain the power equation, that is in terms of Vi cos phi, this minus and this term is being replaced by plus I Vi sine of 2 omega t minus phi minus 90. How we did it? So here also this is a cos term. We replace the cos in terms of sine 2 omega t plus phi plus 90, and this minus when we have to replace, then it is to be omega t plus 90 minus of 180. You can have minus 180 plus 180, so that it is below 180 degree. So we get here 90 minus 180 is minus 90 and 2 omega t plus phi. So this is no longer required. So let us remove this. So we get here the power curve and this PRL. So we will try to have an analysis of it. So let us draw the power waveform looking at the equations. We can draw the power waveform by having the current waveform here, but let us first draw the power waveform looking at this equation. So when we take this equation, this is a fixed quantity. We have here the fixed quantity, then we have a quantity which is variable whose frequency is twice the frequency of omega t. But if it is lagging or leading, how to know? So we can put 2 omega t minus 5 minus 90 is equal to 0, and this omega t we are getting 90 plus 5 divided by 2. So we get here is 45 plus 5 by 2. So positive quantity of 5, so it is actually lagging in nature. So we can get here 45 degree plus 5 by 2. So power waveform will start from here and a sine wave, right? So in a sine motion it will be there, and it will be ending over here the same. So there will be like a punch, or this will be, we can make a baseline in all the places. Okay, so we have explained this thing. Waveform has been drawn, the power waveform. So let us take the example by taking the phi is equals to, let us say phi is equal to 60 degree, or if let us take it like 60 degree, fine. So if I take the phi is equal to 60 degree, so omega t is coming around 45 degree plus 60 by 2, it is around 75 degrees, and it is coming. So it will have like 45 degrees away here. So let us take it at 30 degrees, so it will be better. So if we take it 30 degrees, this will be coming around 45 plus 30 by 2, 15, it is like 60 degrees. So this angle is nearly to be 60 degree. So sine waveform will be there, which is having the double the frequency of the original frequency waveform. So twice the frequency, and in omega t scale it is 60 degree lagging. So from 60 degree onwards, like this will start, and it will move on to the highest big value, that is VIL, and then it will again follow the same. But the thing is that this waveform is having the frequency twice the frequency of the actual line of voltage waveform. So that is why the voltage reference line is dotted line is shown here. So you got the power is like, it is absorbing the power, and positive power means it is absorbing the power. So instead of having a negative sign, we are just trying to get both the things as positive value, so that we can have a physical interpretation of the power. So what we obtain is that the power is, there is the till 60 degree, there is a negative power, then there is a positive power taken in, then there is negative power. And apart from that, this is part 1, this is part 2. And the part 1 is that fixed, the power is being observed, so that power is Vi cos of phi. So you can take that another value is there, which is a straight line, and this power will be like VIL cos of phi. It is always observed. So here you have R and L. So what you can get is that we split into power in fixed value, the part 1, another power which is oscillating in nature. So this power is VIL sine of 2 omega t minus phi minus 90 degree. So that is how we can have a physical interpretation of how the power is being taken by the load, which is of RL type. We will get another picture of it so that we can correlate. Let us draw the same what will the situation here if it is a capacitive load. So here we take the value of omega t plus phi minus 90 degree equal to 0. So omega t is equal to 90 by 2 minus phi by 2, and it is 45 minus phi by 2. In omega t scale it is 45 degree, this is 90, and this is 45 degree. So 45 minus of phi by 2 is somewhere here. So let us make a scaling here, and thinking that your 0 and 90 degree is 0 and 180 degree, because if it is 2 omega t, this will be 180 degree for 2 omega t scale, and this will be 360 degree. So accordingly, let us put a line on the everywhere. This angle is 45 degree minus phi. So that is done. So we will just not write this. So here we have at the same pace we will draw the lines, so that we can easily draw the waveform. So this line will have, let us draw the power waveform here. So the power waveform is drawn, and another one is the Vi cos phi, that is also being drawn over here. So we have a term called VIC cos of phi. So that is a positive quantity, and another quantity is that this is the positive quantity is then VIC sine of 2 omega t plus phi minus 90. So we try to interpret this equation and in terms of the waveform and see that if there is a RC load is there, so what is the power that is being observed. So there are two power is there. Number one is, this is the power VI cos phi, which is always there, fixed power is being observed, and also there is a power get oscillate. This is the second power. So if I find the resultant power out of it, so I need to just add every time these values. So these are the two different powers we have get. Let us try to have a resultant power, and then we can correlate this and the another figure. Now this expression is PRL and PRC has been written once again, and with the difference, so that you can see that we have derived earlier the value equation like this, PRL cos phi and cos of 2 omega t minus phi. So here the same expression is been given again. So just to have a correlation, that this is VI cos phi minus of cos VIL cos 2 omega t minus phi. So same thing is written. So here also 2 omega t plus phi, 2 omega t plus phi, so same thing is 2 omega t plus phi. So what we can do is that earlier we tried to split into two terms, that VL cos phi, one fixed term, one is the oscillating term, and we try to have analysis of this, that what is the power which is getting fixed. But we can also have another analysis of it, trying to get this equation solved, splitting this cos 2 omega t minus phi in terms of cos 2 omega t cos phi sin 2 omega t sin phi. Here we are taking all the active term out, and this is VI cos phi 1 minus cos 2 omega t. This is also changing. This is one term which is changing. Another term is also there which is also changing. Here it's changing with the sin 2 omega t. Here this term is also changing with the cos 2 omega t. Same thing here, when the only difference is that in case of capacitive load, here there is a plus sign, and in case of inductive there is a minus sign. In the previous expression we have drawn the power as a one fixed quantity and one is a alternating quantity. In capacitive also one fixed quantity and an alternating quantity, so that you have a reflection of how does this fixed and alternating quantities are shown, and how the power is being observed. What is the fixed quantity of the power which is getting observed. Here the same fixed quantity but with a variable term is there. Here another fixed quantity with another variable term is there. Let us draw the waveform of this. So here we have drawn the scale of omega t with a reference line with 0 and which is having with pi and 2 pi intersection waveform, and drawn in both the case. So now we have a quantity here, a fixed quantity with 1 minus cos 2 omega t. We have seen this quantity for the R phase while having the power equation for the R phase. Just for the reference, I will take you to the R phase where we have this type of equation. So there for R phase we have developed in the previous video, that if I have 1 minus cos 2 omega t, it can be represented in terms of which is also having the twice the frequency. You just need to change the scale from 0 to some value, and then you can have a sine wave over here with 90-degree phase lag. Or you can have a representation in the terms of cosine, but it is oscillating from 0 to higher value and again to 0. So we can just take this to the same thing. So here also we can have taking this higher value as VI cos of phi. So we can take this higher value as VI cos phi, then we can have an oscillating term here. So this is the oscillating term which is getting, this would look like this. So we have got this reference is there to know that what is actually the frequency wave, and this is 1 minus cos 2 omega t is making this entire thing is like 0 is not 0, and there is no negative term. That is how this is changing. And another term is that is a negative. You can think of making is positive also, saying that VIL sine phi, this is common. And so we have got here this minus of sine we can convert into plus, and sine of 2 omega t, this is, we can negative sign means we can make it plus with plus minus of 180 degree. So here omega t is equal to, if we take this term, it equals to 0, so omega t is equal to 180 by 2, that is 90 degree. So we have got a sine pattern of this reactive value, sine pattern with twice the frequency. So it will start with 90 degree lag, and it will have a twice the frequency. So we will not have this like 90 and 270 degree will not consider as omega t, rather it will be scale of 2 omega t. So we will have one pattern. So let us take this Vi maximum value at certain value here, and let us plot this waveform. So this gives you the idea of that this is the second quantity that you have, is this is VIL sine of phi. This is the peak value, and that you multiply with sine of 2 omega t minus 180, sorry, 2 omega t minus 180. And you have got another quantity that is VIL cos of phi 1 minus cos 2 omega t. So you can write also in this way, instead of writing like this, you can have this quantity is same as the quantity of this minus sign of this. So you can say the plus of this value, the minus sign of this quantity is same as this. So now you can have a imagination of these two terms. One is the term which you can see on this Vi cos phi and 1 minus cos 2 omega t. Another term is this term VIL sine phi sine 2 omega t, negative of this. So this pattern, so this waveform, the waveform 1 and this waveform 2, this waveform 1 and this waveform 2, this waveform resembles with a load which is of R, and resembles load when it is only inductive. So when it is only inductive, you have got this waveform. So this inductive we generally use of have XL, and this resistive was generally with R. So this is so that means we are trying to represent this total power PRL as in terms of if only resistive would have been there. So it is like active power, active component. So active component is now, from here we got active component is VIL cos of phi. Also we get another waveform which is a pattern of an inductor if only there. So this component will be called a reactive. So reactive component is VIL sine of phi, because that's a maximum value, VIL sine phi. So this is the maximum value of the active, this is the maximum value of the reactive term. So similarly let us analyze for the capacitive. So again for the capacitive we have got a component VIC cos of phi 1 minus cos 2 omega t, which is representing without negative value, and the maximum value is obviously here is VIC cos of phi. And we have got another component here that is VIL sine of phi sine 2 omega t. So here also similarly we can say it is starting from 0 and it is having no lag, just 0 in a sine wave. So let us take some value of VIL sine phi, and so that we can clearly distinguish this, and the frequency will be twice of the omega t, it is 2 omega t, right? So in that way the number of cycles will be twice the number of cycle of the actual sine wave. So here we represent So here you have a component, the maximum value is, and this instantaneous value is VIC cos of phi. This is the maximum value, 1 minus cos 2 omega t. Another term we have here, the reactive term, that is VIC sine of phi, and this is the maximum value of this sine wave, and with sine of 2 omega t. So you get here two terms here. Again you got a term with only R if it is they would have there. So that is the active, that is VIC cos of phi. And if you have only capacitor, you could have this reactive term, and that would have, this is a, we can say a capacitive or reactive term. A reactive term, and this is nothing but VIC sine of phi. The difference that we get in inductor and capacitor is that in the capacitor we have got a with the assumption of here, remember that this is assumption here, V angle 0 and I is lagging by an angle of phi. Here in the case of inductive, it is V angle 0 and I is leading by an angle of phi. So with this reference, we are trying these waveforms, and the difference that we observe here is, in case of like active, here also the active is same, only the reactive part in case of inductor is first is like negative, then it's positive. Here in case of capacitive is first positive then negative. So that's the differences we observed. Also going to show you that when we have discussed of only inductor, it is the pattern in this way, and only capacitor we have got a pattern in this way, for the current which is leading here and the current which is lagging here. So these patterns for the resistor, only inductor, and then with capacitor is seen in the combination. Just like here, the combination is R and L, the pattern you can see that, and here R and C, the pattern you can see the same pattern is there. And also we try to illustrate the waveform where we keep the VI cos phi as constant, and then see that how a constant term and what is the term which is getting exchanged. So during the first half, it is like in one cycle there are time when it is taking the power, and there is a time when it is releasing the same amount of power. So the active component, the two term which is coming in this conclusion part is that there is an active term and there is a reactive term. The active term is what get consumed and observed, and the reactive term is get oscillate twice in one cycle from the source and load, between the source and load. The same for the capacitive and same for the reactive, only the difference is here the lagging in nature of the reactive part. Here there's no lag, and then you can get this sine 2 omega t over here, and this is a waveform you get. So this will be very helpful to understand what is the active part and the reactive part. In the subsequent video we will try to do this analysis in the phasor form.